Todd? All right, okay, 2 thumbs up. So that means we're hot. Yeah, he's giggling. That's great. Todd has a hat with 2 moose humping. I don't know if you've seen it. You could, never mind. Anyway, it really does. At the back of his hat, there's 2 moose going at it. It's really cute. These guys are going to talk about why I really enjoyed this talk when I read it in the big list of talks that came through in the CFP. I think I actually giggled, which is kind of embarrassing when you're at your computer at 2 o'clock in the morning. Oh, God. Anyway, they wrote a really interesting tool on a threat that I'm glad that they've been able to actually bring to fruition, to be able to show some of the capabilities that exist in these massive social networking sites and our ability to pass information through them basically unseen. So here's the guys presenting their fantastic SNS Cat tool. I actually have no idea what your names are, so that guy and that guy. So let's hear it, Ron. Thanks. Appreciate it.
All right, well, good morning, and thanks for coming to the last talk. Instead of getting the nice space next door, we'll try to get you out so you can still try to get some nice space for the closing. For our lawyer ninjas, we had to throw something in. This is for edutainment only. And we use Java, which I don't know if you knew, but the old Java EULA said you shouldn't use it on like nuke facilities, air traffic control, but the Department of Energy does use Java on a nuclear plant. All trademarks belong to them. It's our views only. So about us, we do work on a very large network with a lot of users, a lot of data coming in and out. Solomon on this did all of the stego and kind of the GUIs in, and then I actually did the crypto and then the actual architecture. And we have contact if you want to reach us at the end. And that was actually from Hack Fortress last year, but the teams were full. So what we're going to cover, we're going to kind of talk about why this is important, kind of the threat profile and the landscape from events that happened last year. We'll do a quick stego and crypto. We'll talk about the actual problem itself, introduce our tool, have some key takeaways and some defensive tactics. So what sucks about defense is that attackers really, you only have to succeed once. But as a defender, you kind of have to be successful on trying to figure out where your people are at. And how you do that is you reduce your attack surface. And a lot of our argument in this is when you're allowing these social media sites like Facebook, according to them, they allow 250 million pictures every day to be uploaded. That is a huge attack surface to hide in. It's also really challenging to defend against when, hey, you know, how many people on your networks upload to Twitter, upload to Facebook? So the attack surface is critical. So we've seen this. This is kind of a typical attack that we see. This was Night Dragon. So when McAfee put out the defenses for Night Dragon, they said, hey, look for these 2 MD5s on the system. In the packet, look for this constant. And it went to these dynamic DNS sites. You know, from a forensic standpoint, who from your company actually goes to one of these dynamic DNS sites? Also, you could look at, hey, this site was just stood up yesterday or just registered yesterday. A little suspicious. Facebook wasn't just registered yesterday, so, you know, it's a lot nicer than this. The fact is, everyone has secrets. In 2011, you see Manning from all of the WikiLeaks. You see Playboy, who actually had that whole expose leak 2 weeks before put out. They lost opportunity. And then who knows what movie that's from? Anyone? The Shining, yes. That would be your blackmail, maybe, if you were a government leader or someone else, if your secret got out there. Also, the strategic cost. Obviously, with WikiLeaks and the government, there is some strategic loss for losing data. So, insider threat. Who can tell me anything about Ames and what he did here, the significance of all 3 pictures? It was his dead drop, right. So he would actually, when he was spying on the US, he would drop off his stuff, mark that mailbox a little bit up with a line, and that would be the symbol. Hey, there's some secrets here. Soviet people, come pick these up. He used public places to exfiltrate his data. Facebook and Twitter are very public places. So this is the idea. It's a digital dead drop. The attacker never has to see the victim after they exploit him. It goes completely over this. And so the attacker fully masks themselves. And what this does for your firewall and actually auditing it makes you a very sad panda. You want a hug. Just need a hug every now and then.
Okay, so we've talked about attack surfaces. We talked about ways to exfiltrate information from, let's say, a network onto any other site, or to get information off a network so that the attacker can get this offline. So just some audience participation. What are other ways that you can exfiltrate information from a network? Just anything. What was that? Okay, that works well. Anything else? Okay, audio, you can use audio files. Let's say you can start to email information off. You can put it on a USB thumb drive. Hell, you can even print it off and walk out the door with some of the secret information, right? But all of these things kind of have risks inherent within them. Because let's say if you do this and suddenly someone at the security gate is going to pull you down and say, hey, let's have a small search to see what's in your bag. Or you have a lot of documents you're printing lately. Let's go ahead and look at some of that. So perhaps you might be caught if you're trying to exfiltrate information off a network. So that's why one of the good things about our tool is we actually send this information up to a social networking site. It could be Facebook, could be Twitter, could be YouTube, and that the attacker is never, I guess, seen as far as taking the information from the network and putting it out to the outside world. So you put it up to one of the social networking sites, you come off from your own personal network at home or anywhere, you download the images, download whatever you need, and now, poof, now you have your secret information.
So I'm assuming in this room everyone knows what XOR is, so we're not going to go too deeper in this. But the crypto we used in our basic tool, and so you know, we'll get into it later, our tool's completely modular. We didn't hard code one form of Stego or one form of crypto. You can build your own, and we're going to show you later. For our practice, we actually used an exclusive OR. And showing that in practice, it's simple. You just XOR the byte value of your message with the byte value of our key. A lot of companies you'll see will do this, or a lot of attackers will do this with single byte values. Ours can also be multiple. So instead of just doing like 69, our tool, we can say, hey, use 10 bytes, use 100 bytes. So the key length is irrelevant. Why we did that, we wanted to get away from people saying, hey, look for single byte values. The point is, too, I also wrote RSA implementation on this too, so you can use public-private key. We use 2048-bit encryption on that too. So we'll get into that later. But quick Crypto 101, take your message, kind of change it to where it can't be read, and get it back. There's a link if you want to know more. Quick Stego.
Now for a quick Stego. So pretty much the steganography, you know, its lowest derivative, one of the definitions for steganography is that it's going to be an art of hiding data from one media into another, so that looking at it or listening to it or viewing it, you can't necessarily tell that information is embedded within this carrier file. But actually, we've actually put a significant amount of information into this file, and now we're able to get it back. And there are many techniques that exist. You can use bit plane hiding. So let's say an image, it can be layered. So you can put information, let's say the 6th or 7th layer of an image. And so that looking at it, since it's embedded so far back, you might not be able to tell that, hey, there's a little map in there in the back of the image. Or you can use LSB, the least significant bit hiding. And that's pretty much taking the least significant bit from various bytes within your carrier file, implanting some of your bytes from your source information that you want to hide, put it back into that carrier file, write it up to your carrier image, and then send it out. So the product that we wrote is going to use LSB embedding because that's just what we felt like writing this time. And next time, hey, we could have a bit plane hiding, or we can have other forms of media that we want to use. So whenever people think about steganography, sometimes you're like, well, isn't that mainly images? Yes and no, because you can use images to hide your information, you can use media files, you can use video, you can use audio. Pretty much, I'm just taking in bytes, I'm inserting information into it, and I'm writing it back out, and I'm sending it somewhere. That's how we're going to use steganography in our project. And today's demonstration, as we said, will focus on LSB embedding, your least significant bit. And once we write all this information out, we recompose it to a new carrier image, and then we upload it to the website of choice. Now, you might ask yourself, well, if you are changing bits within a file, doesn't that actually change the file? And the answer is yes, but maybe no. Because look over here. As we have just the small blocks, you can't really see the layers inside. But this is just Java. We can use bytes to represent a color. So I just represent a few colors here, 7777F. It's just a byte value for color, and it's going to be a gray. Now, there's nothing significant about 7F. Look at the last two. I was just seated in seat 7F when I was writing the code on an airplane flying to San Antonio. I was like, that might be a good color. So that's how we got 7F. Now, I just want you to focus that on the last byte. Okay, so you're looking at 7F. If we go from 7F to 7E and down to 7D or so, if you look at the image, if you look at each rectangle, you can't necessarily tell that one color has changed from the other. That's because the least significant bit has changed, but yet a gray is still going to be a gray. And now, why is this so important? Because if you're looking at it, you're like, this is pretty big. Fine. But don't forget that we're only changing pixels within an image. And then the pixels are not next to each other. They're scattered random within a file. So if you look at an entire circle of a lot of good pixels, and one might be a slight grade, brighter, you can't tell that something might be awkward. But it's okay, it's okay. So let's have a real example. If you look at the two images, let's have a court case, Exhibit 1 or Exhibit 2. Which one appears to have steganography embedded within it? Just guess. Okay, we have Exhibit 1. Any takers? 1. 1 looks different, 2. Okay, so we kind of have, most people are saying it looks like Exhibit 1. We have a few people saying Exhibit 2. Drum roll, please. Da, 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 da. And actually, there's no stego embedded. It's okay. That's all right. You did well. You did well. Just keeping you on your toes. Just keeping you on your toes. Okay, so seriously, this one actually has steganography in the image. Which one do you think it is? Exhibit 1 or Exhibit 2? Okay, we have a few 2s. We have 1. Anybody else? 3, that's the null. Okay, so actually it's going to be Exhibit 2. And Exhibit 2 actually says, like, this is the carrier file. It has carrier information embedded within the file. Now, if you look at this, you might tell Exhibit 2 might look just a bit brighter, maybe just on the right-hand side, because in this image, we just focused on putting information into the right upper right-hand corner of the image. But you could only tell that this one looks different. Exhibit 2 looks different than Exhibit 1 because you have two images identical, and you're saying this might be different. So, okay, fine, fine, good eye, good eye. So how about we just play Where's Waldo? In all of these images, given images here on your screen, which ones have stego embedded within it? Giraffes. Giraffes, okay. Any others? How about the elephant? Elephant? Polar bear, okay, good. How about the Corona picture? The, Corona drinking the beer? Anything? Any? Okay, so the middle one, and actually the one in the top right, has steganography that we used in steganography to embed information. Everything else is good. Now, why is this important? Because let's say as a network analyzer or a network security engineer, when you're looking at all the traffic on your network, you're like, this image looks like it might have stego in it. It's going to be insurmountably difficult. So that's kind of the beauty of hiding information to certain images and letting all the other images be okay. So steganography efficiency. How much can I really take with stego? As Dan said over here, Facebook, they reported that they received 250 million uploaded pictures a day. Think of the carrier space that we can actually hide information. If we out of 250, maybe 10 or 15 contain stego, how are you going to tell me in 250 million images per day that 10 of them has stego in it? Again, it's going to be quite difficult. And the efficiency of the embedding actually depends upon the algorithm that you wrote to say, this is the byte that I want to embed, or this is the byte that I want to embed. Better algorithms can embed more efficiently within the file. So LSB embedding again, just to recap, as we said, we're going to replace the least significant bit from certain random bytes within the file. We're going to modify it. We're going to take out the last bit. We're going to place our bit from our source information that we want to embed within the file. We're going to write it back out to the carrier, and then we're going to upload it to our site of choice. Now, how good would a demonstration be without some code? You're like, ooh, piece of candy. So hey, piece of code. So this is kind of the code that we wrote, just an overhead pseudocode that is what we actually use within our program. So we're first going to start by converting the source data into bytes. Now, the source data can be a file. It can be text that you copy and pasted into our program. It doesn't matter because we're going to convert it all into bytes. So that's our array that we create. Just embed data, convert source information to your bytes. Then we're going to determine the indices that we're going to place for each bit. Now, this is going to be our populate embed location. In Java, we use the pseudo-random algorithm to generate certain numbers within our file. Because whenever we read in the carrier file, we read it into an indexed array. The beauty about this is I can go from 0, 1, all the way to n, with n being the size of the file in bytes. And then if I just go from like 5, 7, 8, that's going to be an index location of a byte within the file that I can extract. So if I use this, I extract that byte, I change it, convert it to bits, I take out the least significant bit, I implant my own bit that I want to put in there, put it back into the file, and then I write it out again. So now the file is pretty much unaltered with just a few bytes are changed every now and then using our algorithm. That's kind of the beauty of using our pseudorandom algorithm, because we just put in the seed based on the file size. Now we're going to take the embed size, and then we're going to multiply it by 8. The embed size of the source, we multiply it by 8 because for each byte we want to embed, we're going to need 8 bytes in the carrier file to hold each byte. Is that obvious why? Right? Excellent, excellent. I'm getting ahead now. It's obvious because 8 bits is in a byte. Index locations, and then we populate the locations wherever we want to put into the carrier file. Next, more code. Nice, piece of code, piece of code. So whenever we're embedding our bits, we just start and we have like 2 or 3 for loops, and that's it. You first start out, you take your current byte, that's going to be from your embed data. We're going to shift it to the right, logical, all by 7 places, and then we're going to end it by 1. This actually just takes the current byte, puts it all the way in the least significant position, and we end it by 1 to just get its bytecode. Then we're going to put it into an array. We're going to go from 0 to 7, so that's actually just 8 indices. Since we ended it by 1, we now have the bytes code in bits, just 0 or 1 in each of the indexed array positions. Then we're going to go to another for loop on 8 positions, just j is from 0 to 8, 0 to 7. And then we're going to modify it. We're going to take each byte. We're going to, excuse me, we're going to OR it, AND it by FE. So real quick, the hex is, let's say hex goes from 0 to F, not let's say, but hex goes from 0 to F. And so the byte representation, bit representation of an F is going to be 1111, and of an E is 1110. So whenever I take that current byte that I want to embed and I AND it by FE, now if you look at the bit pattern, I now have all of my current bits that were currently in the original carrier byte, except the least significant bit has just been cleared. Okay, so if it was a 1, it's now a 0. If it's a 0, it's still a 0. All right, that's good, that's good. And now our bold, that's kind of like our money statement. This is going to be our foot stomper. So we now have our new byte that we want to embed within the carrier file. We take that byte. Since we've already cleared the least significant bit, we just OR it by one of the positions in our source information that we're going to embed within the file. So since we ORed it, if it's going to be a 1 that we're placing into that carrier file, a 1 is now placed there. If it's going to be a 0 ORed with the 0 is still going to be a 0. Once we do that, we put it back into the carrier file, and then we write it out back to the image. Pretty simple? Pretty simple? Excellent, excellent, excellent. Now, if we're going to extract information from our bytes, we're almost going to follow pretty much the same steps that we chose to embed within the file. We're still going to populate the array. We're going to read in, first we're going to read in the carrier file into a byte array. We're going to populate the locations that we used before. Since in Java we can specify when we use a pseudo-random algorithm to generate my numbers based on a seed. We take the file size as the seed, so now we always get the same values that we represented before whenever we chose to embed. We multiply by 8 because each byte that we extract, we need to take every 8 bytes to represent 1 byte from our source. And then we go into our for loop over here. Now we first start using the modulo. We modulo whatever our index position I by 8. So we can tell if I've already looked at 8 bytes, because our next statement you see by the commented out else. If I'm looking at 8 bytes, I know that, okay, good. The current byte that I'm looking at has already had its position shifted properly. So this is actually represents 1 byte from my original source file. So if I have that, a modulo by 8, and it's not equal to 0, because if you start out at 0, 0 modulo 8 is still going to be 0. That's not exactly what we would like. So we just make sure we're not at 0. Now, once we know that we have the current extracted byte, we save it, and then we just write it out to another byte array of saying this is your original source information. Otherwise, we continue to start shifting. Now, it's kind of a compacted statement, so let's start at the bold. If you look at the locations of index I, that's just the location of where I'm going to extract an index position within the carrier file. Take the index position from the carrier file, go to the carrier byte array, now actually extract that current byte. When you extract the current byte, I'm going to AND it by 1 just to make sure that I have its bit position. It's either going to be a 0 or 1, and now I'm going to start to shift to the left each 1 position. So I do this 8 times, I now have a byte with all of my information composed back together. If there are any questions, just stop us, we can go further. Now recomposing. So after we already embedded all the information that we need into our carrier file, we've written out to our social networking site. Now imagine you go out to the social networking site. This is the attacker on the opposite network. Remember, they never touch each other. So if you are doing forensics on your internal network, you think something has been extracted from your information, extracted from your network, you'll never know that this is the attacker's IP address because everyone is still linking up to Facebook or to Twitter without us ever touching each other. So we're kind of hidden. So at this point, you've just downloaded all of your images from whichever social networking site you chose to use whenever you're running our program. We start by, for each carrier that we downloaded, just put all of these into its own directory. Extract the bytes. Now, once you extract the bytes, whenever you say this is what I'm going to embed, we also make you specify a unique batch identifier. Because if I have, let's say, 1,000 images in one directory, how do I know how to recompose the fragments? This is based on your batch identifier. So I can tell one original source information, one original source document belongs to like 10 carrier files. And another original source document belongs to like 2 carrier files based on the batch identifier. And then we're going to write the extracted information to fragments within its current directory. Now, after we complete all of the images files, I'm now going to take a step back, and then we take a step forward again to reanalyze that same directory. Because whenever we're composing our fragments, we put each fragment into its own batch directory. So analyze each batch directory and say, do I have all of my fragments present from each of the analyzed carrier files? If all these fragments are present, write out the original file. I'm just going to compress it, and poof, there you go, piece of candy. We just got our original source document that we exfiltrated from the network without ever sending that actual source document out. And that algorithm we actually called water to wine because it's like, you know, I'm converting water to wine. Okay, so we continue. Now, you might think that, you know, that was just a little difficult to picture, maybe not. So we just went through a quick pictogram. So the first thing, just as we said, I have all of my images, they're put into a directory. So I take out each image, I extract the fragmented information within each image, and I write it out to its own directory. That's step 1, 2, 3, and 4. Then I'm going to repeat for every image inside my original directory. Then remember, we take our step back, and we take our step forward again, same directory, and now we look at all the batch directories created within that top folder. So for each directory, I look at all the fragments. If all the fragments are present, I now compress it, and there you go. You have your original source file off into your other network.
So the problem scope, as we said, this is kind of post-exploitation. You're already on the system, but you're kind of getting in, and you're at the point where you're starting to evade network detection. And that's where you would want to kind of evade your C2 calls, or if you were defending, try to capture those C2 calls. Lydell Hart, who is a military strategist, actually said, you know, you should never directly go against your enemy. He wasn't actually a German blitzkrieg strategist, and that was kind of the motivation under this. In our approach, we also assumed a reasonable security budget, so we didn't assume they were running like unpatched Windows 2000 or unpatched Windows XP. And they could have a firewall IDS, all of that. It's irrelevant when you allow Facebook and allow all of these other social networking sites to go through with this because we're doing legitimate traffic with these sites. We're just piggybacking on all of that traffic. As we said, we used a framework. It's a modular four-stage approach. You can build your own, or you can use the code we're going to release, actually, and you can change tactics on the fly. So like we said, there's multiple images that we break out into and bring off of. You don't have to send them all to the same account. You can send them to multiple Twitter accounts, multiple Facebook, any combination you want to come from. What that does actually is it makes forensics a lot more challenging now. Because, okay, now they see, okay, this dude looked at this picture on Twitter, looked at it on Facebook. Hey, what's the order? What's the recomposition of all of that? You can change your tactics. You could also throw in a new module, throw that into the picture, send it over, and actually have the framework start reading off of that module so you can get polymorphic in the approach. This complicates defense a lot when you're getting polymorphic, when you're using multiple forms of encryption, multiple forms of steganography. It's language neutral. We did Java because it's kind of a dry erase board language. There's a lot of libraries, so it's easy. But you can write it in any language, really. And This can both be fully automated and human-driven. We chose the human-driven for today just with the GUI, but by all means, I mean, this could be fully automated into bots. So actually going in, kind of like the OSI model, as we said, the 4 parts, the GUI or the command line, which we're writing the command line, that takes in a byte array and throws it down to the crypto module. And whatever the crypto module does is really irrelevant in the framework. It's just, it has to be able to both encrypt and decrypt. It then takes that byte array and passes it to the Stego module. And the Stego module actually preps it for transport. And then at the very bottom, you have your social APIs that actually take those carrier files from the Stego module and put them on whatever sites you want. And social API also writes out your 140 characters or whatever you want to put in there as your Twitter feed. So kind of how it works, for people that like pictures, you send it in the GUI, send it down the stack, it goes all the way down, goes up to one of the sites, and then recomposes. So Solomon will talk over some of the images we have.
This is kind of going to be our images of what our program actually looks like. Whenever you first launch it, this is going to be the GUI. If you chose to use the GUI version, we also remember we have the command line interface that you can just actually type in your commands, and it'll do everything for you. But whenever you first launch it, you choose which module you're going to be loading. So over here, we're going to start out by embedding information into the carrier file. Then you specify other options you would like to put within the program. Whenever you go into your source, actually what we're doing is we're clicking on the tabs to the left-hand side. So you first choose the source file, or you choose that you want to enter in text. So you can copy, paste, type in new information that you want to put into whichever file you wish to exfiltrate from the network. And then you also specify the output directory that you'll be putting saving all of your carrier images. This is your encryption module. So we have the encryption module is specific on its own so that you can specify other options. Remember, we made our program to be modular. We made it also to be as a framework so that if you wrote your own custom encryption module, you say, I want to encrypt information in this manner. You just say, OK, fine, we're going to enable encryption. We're going to import an external jar or an external executable. You load where it is. You enter its information, its key size. You generate keys if that's how you chose to write your program. And then you specify its output directory. Where do you want to save your encrypted information? Because our framework will go in and read it, convert it back into bytes, because bytes in, bytes out, save it out to whichever carrier image, and then we start to upload once we're complete. Here in this section, this is our carrier image. Now, remember we said something we liked was you can take your source information that you want to exfiltrate from your network and embed it into one or multiple carrier images. So we just choose it in one spot. We give you the option to say these are how many bytes that you want to put into each carrier, and then you continue to the next phase, which is where you choose to upload or to download. This is our social API. So over here, right now, we just have it loaded that you're going to be uploaded onto Twitter. So you just put in the login name, that's password, and also whatever tag. Hey, I like this image. I like this picture. I like whatever you choose to say. Our API right now, the module that we wrote, does all this for you. So we made this to be fresh out of the box, simple, click, 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 enter in information, and it's good to go. Finally, our interaction content. So if you are bringing in any external jar files, any external executables, and it gives you information back, we display it over here, just so you have that awareness of what's going on.
So there are conventions, obviously, with it being modular. There's a few things you have to follow. For the GUI or command line, it's really basic. You just have to be able to bring that byte array in. Really, there's not much of a limit. It really depends on this kind of the application of how you link it to whatever you're doing. For the crypto module, we basically have 3 essential flags. The bottom 2 are the same. You just give it the file name and the key file, and you can also tell it where on the disk you want to put it out to. For the Stego module, you have to provide for E, which is embed, your source file, your carrier, and then a batch ID. And the batch ID in his implementation is actually how, when it's recomposing it, the order of the images. So the images actually know what order they're in. It's not a constant order. You couldn't just look at the image or look at them and say, it's actually a dynamic order every time. So there's no constants that are ever placed out on there. There's the X. You want to talk more about this?
Sure. Okay, the X, this is actually just where you specify, this is how many bytes I want to extract from my carrier image. So you specify the carrier image as output directory, it extracts information, and it saves it to the disk. These are going to be your fragments that we spoke about earlier. Whenever we said you want to recompose your information or write information out to fragments. This is how you get your fragments from each carrier file. Now, recompose is to recompose the entire directory. So after everything is done, remember we took our step back, we take our step forward, so we look at each directory that you already have all of your fragments in. So if all your fragments are there, it's ready to go. We compress into one original file, and there you go. Even your MD5s are the same, that you now get your source data back from all of your carrier images. And -G just shows your GUI if you decide to show the user interface. -U gives you usage information, and -H shows your help.
Then for the social API, you just, to upload, it's U, to download, it's D, and you just give it, obviously, username and password. The D, it's actually really challenging on Twitter. I'll talk about that here for a second. So on Twitter, what we have to do is we actually have, we use another open source project, and we pull down the user's timeline. And so the first thing it does is pull down the timeline. And then we look for t.co links, which are the kind of Twitter links that they throw on there to the image site. We then have to expand that because they use it to try to keep spam from getting in there. From that, it sends you to a page out on the Amazon cloud, and Twitter actually uses 2 links out on the Amazon cloud. So we pull the source for that page, and then from that, we essentially grep out the original image. So to give you an idea, it's actually not too challenging if you know how to use grep, but there is some work that actually goes into downloading from a specific username, and that grabs all of the images. And then as we show here, the import external jar, as we said, it's modular, and so there is that option to throw in whatever jar or executable you want on there. Kind of where we're working, ideas that we're still working on, we're porting it over to C and C++. Java's great, but it adds a ton of bloat with all of the libraries and having to deal with the JVM. You take a big performance cut, kind of, and just your file sizes become unnecessarily large. Video and audio, we have Steg for that, and so we're also working on getting the API references for YouTube because there's significantly more carrier space to actually throw it on. Implant development, this was one we actually wrote 2 nights ago, I think, or 3 nights ago, and this was actually the ability to start creating custom implants. So no implants have the same MD5s, you can't just block implants like that, but actually having a custom way to pop those down. We're still working on the host. A lot of this focused on the network level detection, but this is still extremely detectable on the host. We realize that. We haven't done process hiding or any of that. But that would be the idea of your GUI or your command line, whatever instantiation you do there, ideally would have some of that host protection. Also phones. I mean, phones are great because they're not protected at all. There's a lot of space there. So it's not the site's fault. It's essentially, I mean, these are legitimate use of their site. You still, by allowing these sites, do increase your attack surface on that. Signature-based defenses will continue to fail with a sophisticated threat like this. I mean, Night Dragon was successful. They sat there for like 2 years, according to McAfee. But it's hard with signature-based to actually capture certain things when you're going up against a skilled programmer. Not all websites are equal. I mean, Facebook and Twitter, it's a lot easier to hide in. It's harder to hide in those sites that were being used in Night Dragon, those kind of dynamic DNS sites. Because like I said, it's really easy. When was the site registered? Oh, yesterday? You know, why do my users need to go there? Misdirection will continue to be amplified. That digital dead drop. You know, it's worked great. It worked great for Aldrich Games. It'll continue to work great for a while. And applied stego can be dangerous. You know, a lot of people say steganography, you can't hide a lot. I mean, you have extremely limited kind of space to hide in. But our point is, if you apply it the correct way, it can actually be pretty dangerous with pretty dangerous effects. So how would you defeat this? The first, as we said on the host, you have to look at, you can look at what executables you allow to run. Suspicious uploads, so at your boundary level or lower, you can actually see, hey, you know, what's going out, or these random pictures, why are you uploading? You could even do a policy base for the management weenies to kind of say, hey, you shouldn't upload. One we had also, if you have the power, you could also modify the images a little bit. And so if you're working on a smaller image, what if you were to watermark your images coming in and out? That would defeat steganography because we rely heavily on the kind of all of the bytes in that image being accurate. We don't have any error checking or correction. It all has to be exactly how we put it in, which is also a challenge because a lot of social media sites actually do watermark your images when you put them up, which presents a challenge when you're creating your Stego module of, hey, where are they watermarking in this, and can I work around that space they're watermarking? Changing between images, it's the same deal. They all have different formats, and changing formats can actually destroy the Stego within. And then segregating your network, obviously. If you have a more mission essential part of your network, you don't need to allow all of the sites to go there necessarily. So did you have anything else to add on that? All right. So did anyone have any questions, comments, anything? Yes, Terry.
So you talked about exfiltration of data.
Mm-hmm.
If you were to automate this, could you also use the social media sites for command and control of those agents so cascade in both directions?
Right, so the idea would be, and that's the thing, that's a good question, because the question was, have we thought about infill too? And we have. What we send over and the modules that sit on the system can both do kind of the client and server functions. And that's where we said we can get polymorphic, where if we were to request like an upgrade or change it, that's where we're able to both infill and exfil to do that. So
That's also what we're working on with the C2.
yeah, we're working on that C2 part too. That would be the kind of top layer one. Other questions?
Yeah, so a lot of social networking sites resize the images.
Mm-hmm.
Does that mess with this?
Compression will, and that's why PNGs are actually great because they generally won't touch PNGs. JPEGs are a little more challenging. And that's where, when you're actually working on your Stego, you kind of have to work with the sites to figure out, what will this site do? Does this site compress a JPEG? Does it change it? And can I actually get that original image back down? So compression can affect it. We have, let's see, what did you find with that?
Okay, one of the problems whenever we were starting to download some of our images was whenever we first started with bitmaps because bitmaps, uncompressed, bitmaps worked perfect. So we embedded information to bitmaps and then we uploaded it up to Twitter. So then we went back and used our same social API jar file to actually download from Twitter, and then whenever we looked at it, a bitmap went up and then a PNG came down. And so, file formats changed. I was like, oh dear, this is not good. So then I actually tried to put it into our program, and even the file size changed. So just as the question, I think you had it, if the file size changes. Right now, we based our polymorphic algorithm saying, based on the file size, this is what we're going to use for our pseudo-random algorithm to know where we're going to place within the file. So since that file size changed, the location of where we thought a bit would be in that file also changed. But then we got over this by actually writing straight to PNGs. That was just one of the options that you can choose is, hey, do I want to write to a JPEG? Do I want to write to a PNG? Since those are not changed at this time, that worked perfect for us, so we didn't have an issue.
And another cool thing with PNGs is you can actually just append data on the end, and Twitter will actually allow a certain block of data on the end. And the image will display just fine, but you can throw a ton of data on the end of a PNG now, and it actually goes up and will stay up there. So question in the back?
So there have been image Stego algorithms out that are affine transform invariant since the late 90s that are invariant to changes in file sizes, resolutions, because they exploit the perceptual data in the file, not the LSD data in the file. Have you looked at those to be more robust?
Like they said, right now our focus has been on the framework and kind of on this proof of concept, which we are releasing also the source code here in a day or two, and our images. Our demo computer died. We were going to do a live demo computer, but it actually died, and our actual videos were on that. But the idea is with this presentation, we were going to build the framework, and we were going to provide the option for that very thing. So if a user did do research in that, they could just plug their module in. So we didn't implement it, no, but that doesn't mean if you know how to write it or can tie to it.
We also have a spot for custom
Right.
implants that we're bringing.
Question right here?
So I feel like you're kind of cheating on Twitter because they don't actually post images. They have
Right.
other websites that do, which is crazy enough to watch. But where have you actually succeeded? Have you succeeded with Facebook? Have you tried some of the more trustworthy image hosting websites?
So we mainly, we got our proof working on Twitter. We are working on Facebook and also on Imgur, but we haven't gone very deep in that quite yet. So that's definitely something we will, though. So, any other questions? All right, thank you.